All right, so with waves, we said waves carry what? Energy, right? And if it has energy, we know that it has the ability to do work, which means it can hit you, exert a force, and make your body go flying forward, right? So that's our great example of the little kid on the beach, or it's even more funny if it's an adult because, they're not paying attention, right? So they can do work on you. So again, some of those key vocab terms. Wednesday is that vocab quiz. If the wave is carrying energy or it's transferring energy, what it actually moves through, the air, the water, the earth, space, right, describes the medium. So whatever it's actually going to move through is the medium, okay? If it requires a medium, M mechanical, M medium. Mechanical waves require a medium, okay? So sound is a great example of a mechanical wave, okay? I need those vibrations to travel through the air so then you guys can hear me and understand what I'm saying, right? Waves that do not require a medium would be an electromagnetic wave. So on the electromagnetic spectrum, there is radio waves, IR waves, visible light, UV, X-rays, gamma rays. Okay? Some of them have higher intensities. Some have higher energies, higher frequencies, higher wavelengths. One up there is specifically really important, probably starting this week. Anybody see the weather forecast for this week? It's supposed to be hot. It's supposed to be pretty nice. It's supposed to be like upper 80s. So what does summer bring?
Mayflowers.
Sure. That's like rainy April, spring Mayflowers or something like that. It brings heat, but it also brings sunburns, right? Lots of sun exposure. So UV light, if you get exposed to too much UV light over your lifetime, what could you get? Skin cancer, right? When you guys get X-rays, what do they put over your body? Yeah, lead, because they're trying to protect you so you don't get cancer. Repeated exposure to that's really bad. That's why the technician leaves the room. Okay, so that they're not exposed to it. So when we look at electromagnetic waves, some of them can be dangerous to us. Now, radio waves, there's tons of radio waves right now bouncing around our head, right? Can you pick a type of radio wave that we're all currently using right now? What about the iPad? What wave is making our iPads possible right now? Wi-Fi! Yes! Wi-Fi, Bluetooth, airdropping is all made possible because of waves. Thank you, science, for actually utilizing waves because, guys, it makes life so easy now, right? You don't have to hook into an actual landline to have the dial-up. I don't think you guys ever even know what dial-up is.
I don't know how to do it, but I know what
You used to get on the computer and you would sit there for about 10 minutes and it would go, and then like 10 minutes later you would be connected to the internet. And you only had so much time on the internet because it wasn't like unlimited, and it used your phone line so that it cut out your phone line so nobody could call you on the phone line at the same time. Doesn't that make me sound like a dinosaur? But that's how life was back then.
Back when?
Back when I was like in elementary and middle school. That's like what happened. That's what happened.
Late 90s?
It's crazy. It's crazy. No, bro, 2000s. Come on. It's mean.
I was say, I could have been a lot meaner than that.
Yeah, I see how it is.
Industrial Revolution.
Oh, okay.
Christ.
All right, so one way we can classify waves is just whether or not they need a medium, okay? So that would be mechanical electromagnetic. There's another way that we can classify our mediums, and that's going to be specifically, Sean, based upon how the particles move in relation to the wave front, okay? So picture if I attach a string to the wall and I want to make that picture, that transverse wave. What do I have to do with my hand? Yeah, I'm going to move it up and down, but the actual wave will move towards the wall, right?
Yes.
So if you look at the first letter, T, if you look closely, flip that upside down. In math, what shape is that?
It's a
Perpendicular line, right? So when I move my hand up and down, the wave still is going to move front and back or forwards and backwards, okay? So the direction of the particles is going to be opposite. I'm going to show you a simulation here in a second, and you'll be able to see a little bit better. So transverse, if you turn the T upside down, that's how I always remembered it. It would be perpendicular, okay? With longitudinal, you see how it starts and ends with an L? Two L's makes parallel, right? L and L is a parallel sign. If I take a slinky and I push it in, and I let go, it's going to go back and forth, back and forth, back and forth. So on that one, we have our direction. The energy is moving to the right. The actual wavefront moves to the right. And my hand is going forwards and backwards. So since they go together, that means they are moving in a parallel motion. Okay? So on the next slide, it makes it a little bit easier to see. For those watching at home, look at the slides and you'll see the animations. So on my transverse wave, look at this one particle here. Do you see how that single particle is going up and down, up and down, up and down? But follow the wave front. Here it comes. You see how the wave moves left and right? So on that one, because our particles are going up and down, but the wave actually goes to the right, that's where we get our 90 degrees. Okay? Look at the longitudinal one. Find an individual particle, so like that one right there. Do you see how they're moving left and right? But the actual wavefront, the energy, follow it. See it going to the right? So if the particles themselves actually completely moved with the wave, would there be water still there? No, right? So the energy is moving throughout the particles. So the energy can move throughout. It does not necessarily mean that the particles go with the energy. It's just you see that visual move of the water, right? Or of the slinky, okay? So with longitudinal, since they're going in the same direction, they're parallel. Water waves are a little bit different. How many of you guys have ever been to the beach and you're sitting out like in a raft and you go like up and down the actual wave? It's like you go forwards and then you come backwards, forwards and backwards. So you're always back at the same spot. If you follow this blue dot right here, what shape is that making? A circle, right? So that blue dot makes a circle. So whereas transverse makes perpendicular, longitudinal is parallel, water waves are a circle. A circle, okay? So it's a little bit easier for you to see that. If you picture like a buoy as well, a buoy does the exact same thing, okay? So those are just another way for us to classify waves. You guys remember this is from Friday. The top part is called the, bottom is the height of the wave. Crest to crest, trough to trough, start of one wave, start of the next wave. Wavelength. How many waves are up there?
Hold on, give me a second.
There's definitely 1, 2, there's a half, and then what do you guys think that little bit and that little bit makes? Maybe like 2.75-ish, right? So this would be our 1, 2 and a half, and a little bit extras. Okay? All right. Remember, crest to crest, trough to trough, or the start of one wave, start of the next wave. Any subsequent point on the next wave is my wavelength. Since it's a measurement of length, measured in meters, centimeters, nanometers. Okay? However long it takes for that wave to pass is its period. Okay? All right, so on a transverse wave, we have the crest and a trough, right? Because I'm moving the string up and down. If I am pushing the slinky in and then letting go, it's going to smush and come back, right? Smush, come back, smush. So when it smushes, those are where we see higher density of the particles. That's called a compression. Where it then stretches back out, that is what we call rarefactions. And if you notice, it repeats, very similar like a transverse wave, crest, trough, crest, trough, crest, trough. We have compression, rarefaction, compression, rarefaction, compression, rarefaction, okay? And it just keeps repeating because it's a wave, it's periodical, and it repeats over and over and over.
I noticed it says rarefaction, but you keep saying rarefaction.
Rarefaction. Yeah. I tend to slur that word. It's a big, hard word. It's really difficult. Really difficult. All right, take a look. So if you're colorblind, I'm really, really sorry, but we're going to talk about, take a look at those colors. So I have red, orange, green, blue, and purple. All right, so looking at those colors, which one has the highest wavelength or the longest wavelength? Another way to say it. Red. Shortest wavelength? Purple. Which one has the highest frequency? Purple. Lowest frequency? Which one travels the fastest? Thank you. They're all the same speed, right? Do you remember that speed? 3 times 10 to the 8th is my speed of light. Good. Frequency is measured in hertz. Hz, hertz. All right, our electromagnetic spectrum, we'll spend more on the electromagnetic spectrum a little bit later in the unit. But basically, it takes all electromagnetic waves and it arranges it based upon frequency, wavelength, and energy. Okay? So if you look, our higher frequency ones are higher energy, and those are typically the ones that are going to cause us cancer. All right? Lower frequency, lower energy, like our radio waves that are all around our head all the time, not going to cause us cancer. All right? White light, remember we said, can separate out into the different wavelengths. Okay? Even though they combine to form white light, they each have their own frequency and they each have their own wavelength. So again, these are all the key big words. So I need everybody to open their ears. Because remember, vocab quiz on Wednesday. Waves transfer or carry energy, which means they have the ability to do work. We have two types, two ways we can classify them. We can either classify them as mechanical and electromagnetic, whether they need a medium or do not need a medium. Or I can also classify them as longitudinal and transverse. Longitudinal moving parallel, transverse moving perpendicular. Okay? Higher frequency, lower wavelength. If I have a higher frequency, the period is shorter. Remember, period is the time it takes for a wave to pass. Our EM spectrum is arranged, again, frequency, wavelength, and energy. And then so they all are going to travel at the speed of light out in space. Okay? Again, relationships, higher frequency, shorter wavelength. Okay? And same with the opposite. Next would be highest point crest, lowest point trough. Rest to crest or rest to trough is my height or the amplitude, right? Crest to crest or trough to trough would be the wavelength. And frequency, how many waves are passing. Period is the time. And then I think that's it, guys. That is it.